Hi, this is Akash Joshi. I'm the OR guru, and today we're going to be talking about nonlinear programming models, or NLPs. The first example of a nonlinear programming model that we're going to look at is pricing a single good. So let's say that you're a car manufacturer and you're producing cars. You have to consider these things. The cost that it takes to produce the car, so maybe it takes like $15,000 to make one car. I don't know, I'm just throwing out a number here. We'll call this cost variable C. It's not really a variable because it is fixed and it's constant. It's more of a constant, yeah. And then we also have to consider the price. So the price is the decision variable, and that's the thing we're trying to change in order to maximize profits. So we'll call the price P. And then we also have to consider the demand function. So the customers, how many customers are going to buy the car, and that plays a role in deciding the price. So we're going to call this demand function d of p is equal to x minus y times p. This demand function simply relates the sensitivity of customer satisfaction to the price of the car that you're selling. So demand increases as price decreases, and x and y are known numbers that we know ahead of time. I'm just using x and y right now because I don't have numbers at the top of my head. X and y are just parameters; they're known values. Okay, so now let's get into the formulation. So we're trying to maximize this right here. We're trying to maximize profits, and the way we calculate profits is this equation right here. Also, always include p greater than 0. And we know that c, x, and y are greater than 0 because we already know those values ahead of time. So the reason that this is our optimization function, the thing that we're trying to maximize, let's look at each individual part of this equation. P minus C is the sales margin. It's basically like the profit we get per good that we sell. And X minus YP is the demand, or however many cars that we sell. Cars, goods, it's the same thing when I'm saying that. So P minus C times X minus YP is really the total profit, and of course we're looking to maximize profits. So yeah, this is our formulation for pricing a single good. The next example of a nonlinear program model that we're going to talk about is volume in folding cardboard. So let me explain the problem because it might sound a little confusing right now. Okay, so you have a piece of cardboard, right? And you're trying to make it into a box so that it can store stuff. And you're trying to maximize the volume so that you can store more stuff. So in order to make a box out of a flat piece of cardboard that's a square, we're gonna have to start out with the square. We're gonna have to cut off some corners, and then we're gonna have to fold it into something like this. So to maximize the volume, we're gonna have to find out how much of a corner to cut. So let me elaborate a little. Okay, so we originally start with one piece of cardboard, right? And it's a square, so one side is A. We'll call that distance A, or length A. And then right here, we can call this A minus 2D. This right here. This is A minus 2D. And the corner that we cut, the length of the corner that we cut is, we're going to call it D. So everything's making sense. A minus 2D plus D is still equal to A. So it's still a square. It's still a cardboard square. We're going to cut off corners like these, and then we're going to make it into a little box. What we're trying to do is trying to maximize the volume, and we're trying to find out how much of a corner to cut to make sure that we have the most volume and that we can store the most stuff. So once we fold it, these are the values for the box, for the dimensions of the box. So we're trying to maximize the volume, right? So let's talk about the formulation. We are maximizing the volume, as I've said many times. And the way we maximize the volume is we find the volume of this box right here, which is length times width times height. The length and the width are a minus 2d, so a minus 2d squared, and the height is d, so a minus 2d squared times d, and we're trying to maximize that. And we also have to keep in mind that d is an element of the domain 0 to a over 2. That's shown over here. What this means is that d cannot be 0, and it cannot be greater, d cannot be less than or equal to 0, and d cannot be greater than or equal to a over 2. Because if the d was 0, then that means we aren't cutting off any corners, and we can't fold it into a square, or not into a square, into a container. If d was greater than a over 2, that would mean that we're cutting off more than what's allotted in the square, and that would be impossible. So we have to keep this in mind, and this is important for our formulation. And yeah, that's the formulation for a problem like this. The final nonlinear programming model that we're going to talk about today is the facility location problem. I've already talked about this as an integer programming problem, so you can go check that video out. I believe I posted it a few months ago. Okay, so let's get to the problem. There are n cities in a country, and their locations can be shown as xi and yi. I is for each city. So when I equals 1, that's the first city which has a location of a certain number, which could be 1 comma 4. So for example, this one right here could have, this city could be the first city, and it could be, the coordinates could be 1 comma 1. Over here, this could be the 8th city, so it'd be I would equal 8, and it would be, the coordinates would be maybe 6 4 or something like that. Okay, so now that we've talked about that, let's talk about what we're trying to optimize. So we want to locate a facility where the average distance between the cities and the facility is minimized. Let's say that this facility is a hospital. Then obviously we want the distance to be average between all the cities. So if there's an emergency, we can, people can reach the hospital as fast as possible. So let's talk about the formulation next. I'm going to give you a hint here. We're going to use the Euclidean distance formula. If you want, you can take a pause right here and try to figure out the optimization function for this problem right here. Okay, so now let's talk about the minimization function. Okay, so here is the distance between the hospital or the facility and the rest of the cities. For every city, we're subtracting the location, the x-coordinate of every city from the location of the hospital, and we're doing that for y. We're adding it together, and we're taking the square root because that's the distance formula. And this is for every city, so we're adding up all of the distances between each city and the location, and then we're dividing it by the total number of cities, because that's how you find an average, of course. And of course, we're trying to minimize this average. So yeah, that's all for today. Thank you for listening. Goodbye.